morning session. I do appreciate some of us are a bit tired, but just to make sure that we all stay sharp, we have a very nice lineup of speakers this morning. So first will be Edriss Titi from Cambridge and Weizmann. We'll talk about backward behavior dissipative dilution equations. So,
thank you very much. I'd like to thank the organizers for inviting me to this workshop. I would like you also for coming, because it's like toward the end of the marathon, people get tired and many drops. So it is many drops, so it doesn't matter. All right, so my lecture will be about anti-diffusion, as it becomes very clear from later. However, I will prove some rigorous results, and as an applied mathematician, I'm not satisfied with just the result. I would like to see what's the rationale behind it, what's the physics behind it, why? And some I attempt to give explanation a la Cambridge applied math, okay? And some I don't know the answer, and therefore probably you can help in, decipher such results. So let us start from the Navier-Stokes equation, and I'm going to talk about 2D Navier-Stokes equation with periodic boundary conditions. So I'm in a torus in T2. Now, if I consider H to be the space L2, namely of finite energy, but divergence-free functions, then this equation, if it is solvable, you give me initial data that has a solution. The solution exists and unique because I'm in 2 dimensions. Everything is nice. I have a global existence and uniqueness. Unlike the 3D, I will touch upon the 3D and then tell you what's happening there. But in 2D, and now I'm going to call ST to be the solution operator. It's a semi-group. Why semi-group? Because usually I don't have existence backwards of parabolic equations, even though the lecture will be all about backward. But in general, the equation is imposed backwards in time. And therefore, this is semi-group because when I progress in time, I cannot go backward. There is no inverse. So I will call the semi-group S of t of the solution. So you give me initial data, and I look for the solution forward in time. So now Bardos and Tartar, already in 1973, conjectured that if you take the space of all initial data in L2 divergence-free, and you take this initial data with the solution, and you go forward in time, for finite time, what happens to this infinite dimensional space? Because this is parabolic PDE, and it is a smoothing the solution. You start in L2, but you immediately, the derivative is also in L2, and the second derivative in L2. Therefore, you are smoother. Mathematically, one can show that the space of functions, which the derivative in L2 is compactly embedded in the space of functions in L2. Compactly embedded. So why this word compactly embedded is of relevant? Because in infinite dimensional spaces, the unit ball, of course we know from calculus, the unit ball in finite dimensional spaces is compact. But in infinite dimensional spaces, the unit ball is not compact. And therefore, when a set is compact, it doesn't have an interior. Namely, it has nothing with a ball with a flesh. So it's only skeleton. And that's why the image of these infinite dimensional spaces, you go forward in time, it's sort of compact, you lose a lot of things. There's no interior in the image. There's no flesh. Lots of like weeds, if you want, but there is no flesh. So now what they conjectured, yes, even though I go forward in time and I don't get everything, but maybe this weed or this kind of like tree with all these branches is dense in the image. They conjecture that it is dense. All right? This is the Bardos-Tartar conjecture. Now, first of all, the conjecture is still sort of open, but there was some attempt on it. So a weak version of this conjecture was proved by Constantin, Foias, Kukavica and Majda, 1967. Which version has been proved? Basically, that S of t is H is dense, but not in the strong topology of L2, not in the norm distance, but in the weak topology, namely converges weakly in sense of functionals, etc. So therefore, it proved that it is dense, but in a weak topology. So there is a version for it, so there is maybe merit for the conjecture, but we don't know if it's true until this very moment, okay? So there is a version of it which is dense in a weak topology. Very good. So the question is, so far I just told you the problem. It sounds so much like abstract mathematics. Why should somebody ask such a question? Why it is important? It will become clear later. So in fact, they proved even further that if you take this S of t forward in time and take the intersection as t goes all the way to infinity, namely you cut, you see like to the tips of this tree. As t goes to infinity, in fact, this is also dense. Not only for every finite time you are dense, but even if you go the intersection all the way to infinity, namely you forget about the transient, all the way, it is actually dense. That's basically what they proved. So how this is related to the backward behavior, because the title of my lecture, backward behavior, okay, and the Bardos-Tartar conjecture. So basically, to attack this problem, Constantin, Foias, Kukavica and Majda investigated the following problem. So to prove the conjecture, as a byproduct, it was first as byproduct by the following result. Now, you look for a set of initial data, and you say, well, let me stick initial data, and let me take a point in H and see, is it coming from somebody in the past? If every point in H coming from somebody in the past, therefore when I go forward, I hit everybody. And therefore, you want to investigate the set of initial data. When you go backward, it makes sense. But when I go backwards, I don't have existence and uniqueness. So therefore, he says, let me look at this set. It could be empty, but actually it is not empty, because if you're, for people who basically lived during the 80s when people talk about chaos and dynamical systems and so on, so equations like Navier-Stokes, which is infinite dimensional dynamical system, happen to have a compact global attractor. Attractor which is attracted the whole space, and the global attractor is invariant, forward in time and backwards in time and finite. Therefore, there are initial data for which you have global existence backwards in time. So therefore, this set is not empty. And you say, okay, attractor are the set of initial data when I go backwards in time, I'm invariant, forward and back. When I'm backward in time, I remain finite. So they said, let me look for initial data. When I go backwards in time, I exist and exist and exist. But because this is dissipative, because of viscosity, if I go forward, the energy is decaying. Therefore, I go backwards, maybe I'm growing. So they said, let me investigate this set of initial data for which I have existence backwards in time, and I'm growing at most at exponential rate. There is no specification of the rate, but has exponential rate. So therefore, this is the reason why they looked into the backward behavior, because if we show that this set of initial data that I have existence backward, now it's anti-diffusion. Why? Because I have Laplacian, I'm going backwards. Do I have existence backward? And I'm allowed to grow exponentially. If I show you that this set is dense, bingo. That's how they prove it. This is their approach. Okay? So, indeed, so the result is not trivial, because we're talking about nonlinear dissipative PDEs. So why say the nonlinearity is playing an important role? Because you ask yourself the following question. So, however, if I look for linear equation, dissipative, is this set, is it obviously big and large and nice and beautiful or not? Well, the most trivial equation that we know is the heat equation. And I don't get fancy and talk about 3D. It's enough to talk about one-dimensional heat equation and see what happens in this case. So if I look to the heat equation, the solution of the heat equation is basically e to the minus k squared t for t positive. This is the solution of the heat equation when I take periodic boundary condition. And now you ask the question, however, if the initial data has only finitely Fourier modes, then the solution is finite sum here. This is the initial data. And therefore, when you solve, there exists a solution not only for forward in time, but also negative in time. When t is negative, we get exponential growth. But because k is finite, then it is finitely growth. The larger the m, the faster the growth. But I have existence and uniqueness forward in time and backwards in time. And in fact, there's a lot of initial data where backwards in time I exist and grow exponentially. Who are these, for example? All the trigonometric polynomials. And trigonometric polynomials are dense in L2. I rest my case. So for the linear equation, heat equation, everything is fine. And therefore now when you have nonlinearity, now I have to start really sweating to earn my lunch. Okay? So therefore for the heat equation it's trivial. And now what happens with the Navier-Stokes? These people like Constantin, Foias, Kukavica and Majda worked on it, and they proved it in the weak topology, not in the strong topology, for the heat and strong topology. But this is just the beginning. This is the warm-up situation. So these grow exponentially, and therefore they are dense, and therefore if you want, the Bardos-Tartar conjecture is known for the heat equation, but this is trivial. Okay, you don't get a PhD for such a result. Okay. You can publish it, but there's always a journal to publish it, but you don't get PhD for that. Okay, so now based on that, so we look for so this is so somewhat similar to the corresponding linear dissipative equation. So mathematically, an essential element of the proof structure is, I'm just giving you ideas. I'm not going to talk about it in details. So there are two important properties for 2D Navier-Stokes periodic boundary condition. And they have been mentioned in the result of John Gibbon earlier. Namely, if there's no viscosity, you're talking about 2D Euler periodic, you have two quantities conserved, energy and entropy. The entropy is the L2 norm of the curl, or if you want, the L2 norm of the gradient. And therefore, this allows, when you have viscosity, you have forward cascade of entropy, backwards cascade of energy. But these are important quantities which are conserved for Euler. And when you have viscosity, they are dissipated. And as a result, so if I talk about A, so this is for me the Navier-Stokes equation. Many times people see the Navier-Stokes like that and say, wait a minute, it doesn't look familiar. It's just a matter of notation. A is the Laplacian, negative Laplacian if you want. So it's a positive definite operator. If you want, it's like a positive definite matrix, but infinitely many. And BUU, what's B? B doesn't stand not for Banach or anything. It is B for bilinear, because the nonlinearity in Navier-Stokes is bilinear. So you lump the pressure and the nonlinearity by some operator called BUU. So this is a symbolic way to write the Navier-Stokes equation. This is the viscous term, and this is the nonlinearity, and plus forcing outside. So A is basically called the Stokes operator, which is positive definite operator. And now A is like minus Laplacian. And therefore, A to the 1/2 is like half a Laplacian. Laplacian is two derivatives. Half a Laplacian is a gradient. Okay? So whenever we see A 1/2, means I'm talking about like a gradient. The symbol of A to the 1/2 is like K absolute value. And indeed, one can show there's some nice properties here that BUUU equals to 0. This is basically tells you that you have conservation of energy. Like, yes?
Sorry, when you say A to the 1/2, do you mean the object which in Fourier space is the modulus of the wave vector, or do you mean the gradient operator?
No, it's actually, it is the gradient, but if I would like to use what's so-called pseudo-differential operators, it's not the gradient, it's the gradient absolute value. It has symbol K absolute value, yes. But when you look for L2 norms of the gradient, or L2 norm of the gradient absolute value, la même chose, the same thing. And we're talking about norms here. Okay, so there's a property that the conservation of energy, that this is equal to 0, namely the integral of u dot grad u equals to 0 because of incompressibility. And in periodic boundary condition, if you take the integral of u, the grad u, Laplacian of u equal to 0, this is a different manifestation that the vorticity is transported, and therefore when you multiply by the vorticity, it's also there's no contribution. So this is what makes the entropy in 2D Euler is conserved, as well as this is why the energy is conserved. So using these important identities, which are very simple to prove, it's calculus, not more than that, one can show that the energy is, this is the forcing, and this is the dissipation through the viscosity. And now you see the A 1/2, which is basically, if you want, it is like the gradient to the 1/2. And now, this is the L2 norm of the gradient of U, which is the same like the L2 norm of the curl. Because of the incompressibility, the L2 norm of the gradient and the L2 norm of the curl are the same. So this is the L2 norm, if you want, this is the entropy, and this is the dissipation of the entropy, and this is the force. Capitalizing on these and doing a lot of manipulations, it doesn't matter. That's what they use in order to prove their conjecture. In other words, you can see the nonlinearity at this level disappeared completely. The nonlinearity is responsible to the dynamics, but when it comes to energy balances, it disappears. Energy balances of the energy and energy balances of the entropy. And that's why this is a very important feature, which is used for Navier-Stokes, because what mathematicians do, you prove a result, it says, can I generalize it? And then you need to see what makes the first result to work and see if you can mimic, and if you face an obstacle, you try to come around it. Okay? So just basically giving you the essence of the matter. Okay, so note that these energy estimates, the nonlinear part vanishes or disappears. Okay. So now, as I said, we know it for Navier-Stokes. Let me do it for another equation. Okay? As I told you, let's generalize it. So I'm going to talk about an equation which is called the Kuramoto-Sivashinsky equation. I am nearly sure that this equation has been mentioned in this one semester program. If not, then you should blame Rahul. Okay? So what's the Kuramoto-Sivashinsky equation? It appears as a model for the amplitude in combustion theory, or if you look for a fluid in a thin layer of fluid, an inclined surface, this is the amplitude. So U is the amplitude. It's a one-dimensional equation, ut and 4 derivatives. So this is bi-Laplacian. You have been seeing bi-Laplacian in Swift-Hohenberg and in Kahn-Hilliard and all kind of this. So this is bi-Laplacian plus uxx. Anti-diffusion. Okay? So there's anti-diffusion here, plus nonlinearity ux equal to 0. Now this equation happens to be a dissipative dynamical system. Now wait a minute. If I forget about the nonlinearity and I'm periodic with period L, then for low wave numbers, the uxx is much stronger than uxx. Because this gives you growth like k squared, and this gives you decay like k to the power 4. When k is small, k squared is stronger than k to the power 4. And therefore, for low wave numbers, if I forget about the nonlinearity, the solutions grow exponentially. And for high wave numbers, what happens? The solution decay exponentially. Okay? So let me take a picture here. Here are the wave numbers. There's some critical wave number depending on the period L, such that here I have input of energy to the anti-diffusion, and here I dissipate energy because k to the power 4 bigger than k squared. And therefore low wave numbers grow, high wave numbers decay. But I claim that this equation is dissipative, namely that no matter where I start from, the solution eventually decay and get into balance. They get into some kind of absorbing ball, into a ball in the space of solution where I remain bounded. So there's balance somehow. Wait a minute. Where the hell is the balance coming from? I have shown to you this is growing exponentially if I'm low wave numbers, and this is invariant. And high wave numbers is invariant decay. So how could this balance happen? Now, I would like to look to the UUX. We know from Burgers' equation, UT plus UUX, this is an equation which we teach for undergraduates to show something about interesting dynamics of nonlinearity. This equation develops shock in finite time. So the nonlinearity tried to form a shock. What does it mean, a shock? This equation, the energy is conserved all the way up to the shock. But then, at the shock, the energy breaks, but energy is conserved. What does it mean, shock? A shock means I have sharp gradient. It means I put energy in the high wave numbers, which is multiplied by a factor of k because of the gradient. In other words, UUX is cascading energy from low wave numbers to high wave numbers to form a shock. In other words, UUX is a highway that transporting energy from the anti-diffusion to the diffusion, and therefore you produce energy, you transport it through the nonlinearity, and you kill it, and now the whole orchestra playing together beautifully, and you have dissipative dynamical system. It's interesting because many times we think about the nonlinearity as the bad guy. Guess what? Without the nonlinearity, I don't have dissipative dynamical system. It is helping me to stabilize. Huh? So this is the Kuramoto-Sivashinsky, okay? And now, because it is dissipative dynamical system like Navier-Stokes, can one prove the analog of the Bardos-Tartar? If I start with initial data in L2, is the image, because I have global existence, is it dense? And now this result has been studied by Kukavica and his student Malcok. Basically, one has to look what happens to the backwards. Wow, surprise. If I start with initial data, which is not in the global attractor for the Kuramoto-Sivashinsky, because if I'm in the global attractor, I have existence backwards and I remain finite, because I remain within that ball. But if I start initial data outside this attractor, and I try to go backwards and ask myself, do I have solution that they grow exponentially? Answer, no. Anybody outside the attractor, when you go backwards, boom, blows up in finite time. Boom, unlike Navier-Stokes. And then you ask the question, so what's so special about Navier-Stokes? Why every equation, why this equation, when I go backwards, I blow up in finite time? Okay, by the way, when I go backwards, the anti-diffusion becomes diffusion, but this guy becomes big anti-diffusion. So, what happens in this particular case? So UX is amplifies the low wave numbers while this is damping them, so when you go backwards, things becoming unbounded, and the result of Kukavica and Malcok proves that this equation, the Bardos-Tartar conjecture, is not valid for this equation. I cannot generalize it. Okay, so now you ask yourself the question, okay, Kuramoto-Sivashinsky too difficult for me. Let me see something simple like Burgers equation with viscosity. Because I'm trying to understand why Navier-Stokes works. What's the mechanism other than the proof and entropy, etc.? Is there some other things? So you ask an equation which is simpler than this equation, which is the Burgers equation with viscosity. Now, Burgers equation with viscosity forward has global existence because the viscosity smoothes the shock, etc., etc. And now you ask yourself, what happens when you go backwards? Can I show that initial data? Now, notice that the attractor for this equation, because there is no forcing, is 0. Everything decays to 0. So the attractor is 1.0, and it's steady state. Therefore, what one can show, if you take any initial data different than 0, and you try to go backwards, you ask, can I extend it infinitely in time, but then grow exponentially? And the answer, no. Every initial data other than 0, boom, blows up in finite time. Now, okay. I have been seeing that UUX is forming a shock. If the initial data is like increasing and decreasing, because I don't want it to be average 0, okay? So like something which is interesting. So the initial data for this, when you go forward, blows up. When you go backwards, it also blows up. So therefore you say, well then, am I fool? No, here it's easy to explain. Because without this term, which is when I go backwards becoming anti-diffusion, the equation tries to blow up. You add more instability, more anti-diffusion, and therefore, for sure it will blow up. So what's the surprise? And then you can say maybe similar thing happened to this equation, because this is trying to blow up, and you have this, eventually you have anti-diffusion at the high wave numbers, so you enhance the singularity. So therefore, naively you think, the whole thing is not because of the viscosity, it's because of the inviscid flow in Burgers blows up in finite time, forward and backwards in time, while for Navier-Stokes, if I drop the viscosity, I have Euler in 2 dimensions, I am okay. Forward in time, and backwards in time. And therefore, wow, now I understand what happens in Navier-Stokes equation. Because the implicit case does not develop singularity, and therefore the anti-diffusion at most will give you exponential growth like the heat equation. Well, this, the nonlinearity blows up in your face, and therefore you put an anti-diffusion, and therefore it should blow. Okay. This is a scenario which says, okay, you rest your case, I have explanation, and I'm happy. Then you ask the following. So this is what I said to you just a minute ago. So motivated by this scenario I told you, let me look at an equation which is okay forward in time and backwards in time. I know Euler. Do I know equation like that? Like Burgers, KdV? So the KdV, because of the dispersion UXX, has a global existence forward in time and backwards in time. And if I am correct that basically the reason in Navier-Stokes things work, because at the Euler level, I am fine forward in time and backward in time, let me take KdV, add viscosity, and let me prove Bardos-Tartar conjecture. Yes?
Sorry, is the conjecture also true for forced Navier-Stokes?
Well, yes, the result about Navier-Stokes is forcing.
So, but then the way you argued about the cascade, in the forced case, the cascade is in the opposite direction, right?
Yes.
And
yeah.
then still it doesn't...
Yeah, it's okay. It's still okay. Okay, it grows exponentially. So. And by the way, I mean, there's this issue about, don't forget, I'm talking about Navier-Stokes periodic boundary condition, and I'm assuming that everything has mean zero, spatial mean zero, which means the wave number 0 is not part of the solution. Therefore, yes, you have inverse cascade, and then people say, yes, I accumulate, therefore it's going to keep accumulating. This is a wrong scenario. You know why it's a wrong scenario? Because people always think about what happens in the whole plane. The whole plane, you don't have limit. So what happens if I am in 2D Navier-Stokes and I have a box? I am in a box, then the periodic boundary condition, and then you start with something small, and it's growing and growing, and people say, oh, I'm accumulating the energy. Well, there's no mechanism to dissipate energy at at low wave numbers, namely at high scales. Do you think so? Yes, there is. You don't see it in the equation. It's not a term in the equation. It's the dynamics, ladies and gentlemen. Periodic boundary condition, it's not Navier-Stokes or an equation in a box. It is in the whole plane. And what you see in this box, you see in this box, you see in this box. Navier-Stokes periodic or an equation periodic is in the whole plane. And therefore, when you see this eddy going this way, becoming very large, it is the same, very large. And hence, because it is oriented in this direction, here it is oriented in this direction, and it cancels each other. Therefore, the flow becoming dissipative of itself. I don't need to have a term in the equation. And that's why, yes, you have inverse cascade, but it stops by the flow itself. I don't need to put hyper-viscosity to see that. People put hyper-viscosity, you know what? To accelerate things, to converge to statistical equilibrium. They don't tell you that, but I tell you. Okay? So, does this answer your question conceptually?
Okay, now I'm confused.
That's the purpose, so I'm confused. Is there another one? Anybody want to conquer? Yes.
In the periodic box, when you simulate forced homogeneous isotropic turbulence, you don't get one vortex, you have two, just to satisfy the periodic box.
Yes, fine.
So that argument would not hold.
Well, no, because if you have here's a box, and you have two here, then you have two here.
Yes.
And this is going this way, and this is going that way. And because they're together, one goes against each other. And by the way, when you have a flow going this way, the other going this way, how do we call this flow? Shear flow. And you know what's a shear flow? Shear flow means producing large gradients, namely small scales. And boom, that's now the viscosity comes and kills it. Do you see why the flow slows itself? Because I create shear flow, which creates a small scales by the mere shear, which is basically the viscosity. Now act, do it. Are you still confused?
Yes.
Okay, well, we talk about it later. So maybe you need more coffee.
Yeah, it's not satisfied boundary.
Okay. Which boundary condition? There's no boundary condition. This is periodic because it's the same flow. Periodic means, look, you know what periodic means? I'm in this room. It means if I put my hand from here, I can scratch my back from there.
Yeah.
That's what periodic. This means there's no wall. These are artificial wall. I put my hand comes from the other side, scratching my back. So therefore, this and this are the same. But this is going this way, and this is going the other way. Because you live on a torus.
We'll talk.
We'll talk. Okay, very good. Very good. So, let's continue. So therefore, I would say, okay, let me look for an equation which is like Burgers, but has existence backward and forward. And this is the KdV with dispersion. It has a global existence and uniqueness because of the dispersion, forward and backwards in time. And then you say, let me add viscosity and see if I can prove the conjecture. So I add this viscous term, and then I look to this. What is the backward behavior? Because I would like to see, if I take the space of initial data and I go backwards, can I have solutions grow exponentially? Guess what? No. All initial data, other than 0, because the attractor for this equation is only 0. If I take initial data whatsoever and I go backwards in time, boom, I flow up in final time. So I don't have solution exist indefinitely in time growing exponentially. So therefore, my explanation to you that why it works for Navier-Stokes, because Euler is okay backward and forward, here's an equation which behaves good forward and backward, and it does not work. Then my explanation, sorry, did not hold ground, and therefore I need help. What happens? Why Navier-Stokes works and does not work for this equation? So I'm going to give a scenario, and that's where basically you as a physicist can really give explanation. Why one equation works, why does an equation does not work? Okay? So the answer, as I said, either the solution do not exist or they blow up in finite time. This is the backwards. Okay.
Very question. This KdV with Burgers, it has actually two different solutions depending on what the viscosity. It can be oscillatory still or can be dissipative.
No, because you have viscosity, it's all dissipated. The energy goes to 0 and go forward in time. Because I start with average 0, spatial average 0, and therefore everything dissipated. Because I have this new viscosity. KdV alone does not, because it has conservation of energy, has solitons, etc. But with viscosity, when I go forward, it decays all the way to 0. The attractor is 0. If I take anything up from the 0 and try to go backwards, it blows up. And this is surprise. The blow up is not because of the nonlinearity, because of the shock. There's something else, because UXX with UX is like neutralizing each other by dispersion, or averaging, whatever you want to call it.
How about the conservative quantities for oil?
Yeah.
Without the viscosity?
Without the viscosity, yes, they are conserved. But now when you add viscosity backwards, anything conserved becomes anti-conserved. This all works about anti, which means anything which was like under control, it loses control.
But each conservative quantity is...
With the viscosity backwards, it becomes unconserved and trying to blow up in your face.
Well, but okay, it's not conserved, but decay rate or...
Does not decay because you have anti-diffusion. It grows.
Yeah.
Whatever was decaying will become growing now because you're going backwards. So the viscosity backwards or the anti-diffusion backwards not only does not enhance, it enhances the growth of these conserved quantities. In particular, the energy will become growing and growing and growing. For example, if you take the energy balance, you will see that the energy will be growing. Okay, so what happens if I look at this equation when I add this term? So I put viscosity, this is basically sometimes called the KdV-Burgers-Sivashinsky with beta. One can show that when you go forward, it has an attractor, and the attractor, like there's a ball in the space of solutions with radius rho in L2. That rho behind like L to the power 5 halves of the period, or if you take the parameter viscosity, like 1 over nu square, so when nu goes to 0, it becomes infinite, or it's like beta to the power 5, so when beta is very, very large, because this is instability. It's growing, and so on and so forth. So this is, for this equation, when I go forward. And now what happens, when I look to the energy balance, this is the energy balance, the nonlinearity disappears, the dispersion disappears. You have a fight between the viscous term and the instability term, which is anti-diffusion from the beta, if beta is positive. And now you have fight between these two terms. There you can use Cauchy-Schwarz and Young's inequality. And therefore, if you think about it by the energy balance, you can see you have a new lambda 1 to beta. This is the energy balance for this equation forward in time. And this is bad because if nu is very small in comparison to beta, I cannot prove that the energy under control. And this is the most naive approach for this equation. Now, why it's the most naive approach? Because I did energy on U directly. Namely, I tried to do energy on this equation without taking into account the nonlinearity at the energy level disappears. But I have been telling you that the nonlinearity is stabilizing. So I need to take advantage of the nonlinearity. And I couldn't take advantage of it. So what's the idea? The idea is to follow what Goodman has suggested. And to do that, basically, one has to take advantage of the nonlinearity to show that there is a stability. And what Goodman suggests is, say, let's take a background gauge function phi. Instead of looking to the L2 norm of U, I look for the L2 norm of U minus phi. Namely, instead of taking a ball centered at the origin, centered at some well-chosen function phi, background. And now, this function phi, I mean, again, I'm waving hands to go very quickly. One can show that if you choose phi to be almost like alpha x, periodic, of course, alpha x is not periodic, so near the boundary you have to do some massaging, okay, some cosmetic surgery. But so phi x is like that, and if you take phi x like that and you do the balance, you discover that u minus phi squared satisfying this relationship, and you know this and this are competing. This is basically growing and this is decaying. But now if you choose phi prime to be like alpha, therefore you get here alpha u squared and you have beta u squared. So if you choose alpha large enough, this kills that. That's the idea about this background situation. And this took advantage of the nonlinearity because when you take shift by phi, the ux, you give you contribution phi ux and u phi prime and so on and so forth. This is just part of the proof, okay? So now, so the idea of the proof is to show that blow up backwards of this equation. So what Kukavica and Malcok said, basically, again, I'm giving you some idea of the proof. I'm not going to prove it. So the idea of the proof is you take your space and divide it into dyadic shells. 2 sum are 0, 4 times are 0, 8 times are 0. And you look to the equation backwards and you see how long I can stay in the shell before I move to the next shell and to the next shell. And you estimate the times. And what happens that you see that you are really going from one shell to the other, within certain definite amount of time. So you need to do analysis to estimate the time. And you continue that, and then when I add over all the shells from 0 to infinity, you discover that the sum of all the time that you spend in every shell, it is basically a converging series. This means that within finite time, you go all the way to infinity. You leave all the shells. That's how you prove the blow-up. Just giving you an idea of the proof. So you divide the space into shells, see how much I stay here, how much I stay here, how much I stay here, and each one is a very different amount of time. When you add all these times, it's a converging series. This means within finite time, I go all the way to infinity, therefore I blow up in finite time. That's the idea here for the proof. That's basically what I share, and I don't want to talk about more details, but it doesn't matter. This is the situation. So now, I would like to talk about KdV and try to understand what happens. So you cannot talk about KdV without talking about solitons. Okay? Some people will be insulted. Okay? So KdV has a well-known solution, which is solitons, which are typical solutions of the KdV. So if we take a soliton as initial data, then it remains solution. Now, so following the classical work of Gardner, Greek, Kruskal, they invented method of what's called inverse scattering to investigate the KdV equation to solve the KdV explicitly. So they look at this KdV, like factor here 6 just for to simplify things, either periodic or on the whole R. Now, if U is a solution of this equation, and you look to the operator, to the spectrum of this operator, one can show that the spectrum of this operator is, the eigenvalues are time independent, but the corresponding eigenfunctions time dependent. I'm just basically reviewing what's known about KdV from times when before I was born, okay? So now, so we look at this particular situation. Now, if you look to the KdV with perturbation, now I'm using hand-waving physics arguments, do perturbations. One can show that this scenario of inverse scattering, etc., if you look at this equation when you have perturbation, the eigenvalues when epsilon y is equal to 0 were constant, time independent, but now when you have some perturbation, they have the time dependent the eigenvalues. Lambda prime is like the integral of psi square q, when psi is the corresponding eigenvalue of lambda, and we know that psi time dependent. And therefore, the whole idea to see what's happening here. So we need to see the evolution of lambda. So I can take the typical soliton is given by this function with L0 is a length scale. So basically, this gives you the width, and this is the height. And as a result, you basically, the corresponding eigenfunctions are like these. This is basically the soliton solution. And now, if you look for the length scale in time, this is the corresponding for the eigenvalues, different eigenvalues. The lambdas the L's are depending on time satisfying that. So now, what can show is that the eigenvalues for the perturbation is like lambda t, and the psi is like this. And when you look for perturbation, L prime satisfying this relationship, because this is the psi, and this is the q. So now I have different q's, different operator q. So if q is like a multiple, like damping, not viscous. KdV equation with damping, if I go forward, I decay. If I go backwards, I grow exponentially because there is no, I don't excite the high frequencies. So I'm like almost like, and therefore, you can see if you take this particular situation, you can show that L prime is like L, and therefore when you go backwards, the L is growing exponentially. So the amplitude of the solution grows exponentially, and the width is shrinking exponentially. That's why if you have damped KdV, you are okay. If you have viscous KdV, you're not okay. Please, I'm trying to give explanation what's happening. Now, what happens if you add viscosity? So when you add viscosity, namely epsilon q is like epsilon u x xs, the L prime satisfying this equation. And now L prime, L cube, everybody knows that when you go backwards in time, boom, blows up in finite time. Which otherwise the amplitude of the solution blows up, and the spectrum, basically, sorry, the width of the solution goes to 0. So becoming very narrow, becoming like what? Like a delta function. So this is at least from hand waving or asymptotic techniques to see why KdV is not working. Okay? Other than I gave you rigorous proof, why? So I gave you an example. And now, further explanation, where I probably would need your help. Okay? Because the solution behaves like, in some sense, backwards, like basically like a delta function, then you say, you know what? Let me look at the energy spectrum. So because it's like a Dirac delta, the solution, we know that the energy spectrum is almost constant for small wave numbers. And for high wave numbers, it's basically different because I have the solution. It is like a delta, it's not a delta. And therefore, the spectrum is approximately like constant. Now, and for wavelengths, in some sense, which are basically small enough. For large ones, it is not. And as a result, you can say, on the other hand, I would like to compare, because I've been telling you why it works for Navier-Stokes. I gave you rigorous proof there, I give you rigorous proof here, but I want to understand the physics behind it. If I look to the energy spectrum in the Navier-Stokes equation, the energy is like, because of Kraichmann theory, is like k to the minus 3. And when you add or integrate in the wave numbers, here you get summation of k squares in this particular case. And this is much, much larger than summation of 1 over k, which is like ln k. And that's why for Navier-Stokes, you can handle the energy spectrum, while for the KdV you cannot, because it's basically very bad. At least linearizing around particular solution. this is another attempt to explain the result, the rigorous result, trying to use the physics. Okay? Again, this is an attempt. You help, maybe you have better explanation, and so on and so forth. So now, let me move because I don't have much time. So another equation, which is the complex Ginzburg-Landau equation. Okay, the complex Ginzburg-Landau equation, the nonlinearity, which blows up as we go backwards in time. So it looks like Burgers, and therefore, most likely, I will not have the Bardos-Tartar conjecture here. I've tried using litmus tests in some sense. So the complex Ginzburg-Landau equation, which is another dissipative system, forward in time, backwards in time, I have blow up in finite time. Okay, so now, I told you I would like to make a comment on 3D. Many people, when they did computations for Navier-Stokes, in order to stabilize things, they take Navier-Stokes with hyper-viscosity, Laplacian square. Now, this equation has a global existence both in 2D as well as in 3D. So why I'm investigating this, I says, oh, maybe I can prove the Constantin, Foias, Kukavica and Majda result for hyper-viscous Navier-Stokes in 3D. We failed. We don't know how to prove it. Doesn't mean it's not correct, but we don't know how to prove it. Even in 2D, we don't know how to prove it. Wow, it's really strange. Like viscous is okay, but hyperviscous is not okay. So, I don't know why. I need help. Why? I mean, what's the physics? Why do you think the physics of 2D hyperviscous is different than the physics in which, in one hand, I have basically the Bardos-Tartar conjecture is correct for one case, but not to the other one. Well, the other one is not that correct. I don't know how to prove it. So maybe there is some underlying mechanism that basically somebody can convince me, don't even try. Or should I put a row of PhD students, one after the other, to break their bones? You know, after 6 months, it's okay, you cannot do it. Okay, let's go to another problem. The next guy in line. Should I do it, or should some physicist convince me like you are really barking on the wrong tree? So that's where I need help. Why for this equation? Now, what we can show, and this is just a result, that one can take a space of initial data for which, in some sense, some initial data, not all initial data, and this class of initial data is not dense in H, for which I know that for the hyperviscous equation, I have exponential growth. So there is a lot of initial data for which I have exponential growth, but this lot of initial data is not dense. I want it to be dense. So there is hope, but it's very partial hope and it's very weak hope. Okay? And I think I should stop here. Thank you very much for your attention.
Thank you. Questions? Yes, please.
Random speculation of a physicist who did not understand most of the things you said. For the
You didn't understand everything?
No, I mean, the difference between 2D and 3D
Yes.
in Navier-Stokes, a
Yes.
very important difference from a physical perspective,
Yes.
is in 2D, the vorticity direction is discrete. The vortex is either this way or that way, so it's up or it's down. But in 3D, it's everywhere. So I'm going from some variable that was discrete to some variable that is now continuous, and that changes the physics of the flow dramatically. I don't know what it does to the math.
As I told you, I cannot prove the conjecture with hyperviscosity even in 2D. So the vorticity stretching term that you
Oh
took.
no, of course you can't. I'm talking about your hyperviscosity model.
Yeah, hyperviscosity in 2D. I don't have to prove it.
You don't know how to prove existence for...
No, I have proved existence and uniqueness. That's not a problem. But I cannot prove the Bardos-Tartar, the backwards. But for 2D, I could. That's my question. So it has nothing to do with the vorticity stretching, because even in 2D, I have an issue. This is the first thing. Now, this is some news. Let me give you another news. Professor Gibbon mentioned the difference between 2D and 3D is the vorticity stretching, and that's why in 3D we cannot control. I have some news for you. And the news is the following. If I look for the Navier-Stokes 3D in a pipe, infinite pipe, and I look for solution with helical symmetry. So they are three-dimensional with helical symmetry. I have global existence and uniqueness. And the vorticity stretching, not trivial. So the issue of the vorticity stretching is the obstacle when we try to prove in general, we're facing it. But it is not the full scenario. There are flows for which the vorticity stretching can be as large as you want, but still you have global existence.
Good job putting a physicist in her place.
You know what DAMP stands for? Applied Math and Theoretical Physics. So I'm trying to learn from my colleagues, theoretical physics.
Anyone else?
As I told you earlier, I mean, if I have mathematical results, I need to understand the physics behind it. Otherwise, I don't get the full satisfaction. It doesn't give you the full picture.
In your hyperviscosity case, can you combine the Laplacian and the bi-Laplacian, because you have the result for the Laplacian? Can you perturb around that?
Well, we tried that. It's not like we didn't try. We tried that. The problem is that there are certain quantities in which there's some kind of like balances up to the viscosity term, but not the hyperviscosity between the entropy and the energy. And this is important for the proof. But this is a technical aspect. It's not like we didn't try. We tried that. This is a technical aspect, but not more, not less. Yes?
Can anything useful, is there any interest in the 1D actual Navier-Stokes case? Obviously not incompressible. 1D compressible with some simple equation of state like constant speed of sound.
Many people call this Burgers equation.
Well, no, there's a density as well.
It's one-dimensional and it's compressible, and then the same thing.
No, but there's a velocity and a density. So
You want it like a couple. I mean, one can try. One can try. If there is some interesting problem to be done, yes, one can really investigate that. But that's why we studied burgers, because many people think about burgers like the analog of, but then we see that it's completely out of the,
I mean, that's why I mentioned
sure.
with the density.
Okay, we need to move on. Thank you so much.